At 6:05 p.m. on August 1, 2007, an 8-lane interstate bridge full of rush hour traffic dropped 108 feet into the Mississippi River.
The physical parameters of this event were thoroughly documented in the subsequent investigation. Quoting verbatim from page 13 of the National Transportation Safety Board Highway Accident Report, about 6:05 p.m. Central Daylight Time on Wednesday, August 1, 2007, the 8-lane, 1,907-foot-long I-35W highway bridge over the Mississippi River in Minneapolis, Minnesota, experienced a catastrophic failure in the main span of the deck truss. As a result, 1,000 feet of the deck truss collapsed, with about 456 feet of the main span falling 108 feet into the 15-foot-deep river.
On the day of the collapse, extensive roadway work was underway on the I-35W bridge. 4 of the 8 travel lanes, specifically the 2 outside lanes northbound and the 2 inside lanes southbound, were completely closed to traffic. Vehicles were being routed through the remaining 4 open lanes during the peak of the evening rush hour, which subjected the partially closed structure to heavy, bumper-to-bumper commuter traffic.
Section 1. The moment of collapse. The physical state of the structure was actively being altered by Progressive Contractors Incorporated, the firm tasked with repairing and renovating the deck. This project required removing the existing concrete wearing course to a depth of 2 inches and adding a new 2-inch thick concrete overlay. The pre-existing wearing surface remained in place on the 2 inside lanes northbound, where the average deck thickness was 8.7 inches. The new overlay was already in place on the outside lanes. However, the surface of the 2 inside southbound lanes had been milled for the entire length of the bridge, removing approximately 2 inches of material.
The human and structural toll of the collapse was immediate and severe. 13 people died, and 145 people were injured. A total of 111 vehicles were documented as being on the portion of the bridge that collapsed. Of these, 25 were either construction vehicles or vehicles belonging to construction workers. Furthermore, 17 of these vehicles were recovered directly from the water.
In preparation for the evening's concrete pour, heavy construction equipment and raw materials were staged directly on the deck truss. In the early afternoon, construction equipment and aggregates, sand and gravel used for making concrete, were delivered and positioned in the 2 closed inside southbound lanes. These aggregates were staged toward the south end of the center section of the deck truss portion of the bridge, and they were fully in place by about 2:30 p.m.
Section 2. Contributing construction loads. A forensic breakdown of the specific loads on the bridge reveals the precise weight distribution on the structure at the time of failure. The weight of the concrete that had been previously milled from the 2 inside southbound lanes was calculated by the Federal Highway Administration to be 585,000 pounds. Approximately 250,000 pounds of that removed weight came from the bridge center span. However, this reduction in dead load was offset by the new staging of materials directly above the critical sections.
The sheer volume of the raw materials delivered to the site was substantial. As stated verbatim on page 28 of the NTSB report, the documented delivered weights for the aggregates staged on the bridge were 184,380 pounds of gravel and 198,820 pounds of sand, for a total weight of 383,200 pounds.
These figures represent only the aggregates. The estimated weight of the parked construction vehicles, equipment, and personnel in this specific area added an additional 195,535 pounds. This created a concentrated load of 578,735 pounds positioned over the inner west side of the bridge center span, just north of Pier 6. Factoring in the loads south of Pier 6 and north of Pier 7, the summary of approximate loads shows 712,326 pounds total, resting solely on the closed southbound lanes.
Geographically, this weight was highly centralized. The aggregates and associated construction vehicles came to occupy an estimated 228-foot-long section of the 2 closed southbound lanes over the main river span, designated as Span 7. The materials were situated closely together to facilitate the concrete pour that was scheduled for 7 p.m.
Following the accident, the Minnesota Department of Transportation analyzed this specific load configuration. Referencing the department's post-accident admission regarding the concentrated stockpile, the NTSB report documents their findings on page 28 with the following direct quote: "This loading is immediately seen to be much larger than design loads."
Section 3. The gusset plate failure. The forensic investigation isolated the specific physical failure point in the truss structure. The collapse sequence was traced directly to the gusset plates at the U10 and L11 nodes. Gusset plates are thick steel plates used to connect the structural members of a truss, such as upper and lower chords, diagonals, and verticals. The finite element analysis and physical wreckage indicated that the initial fracture occurred in the U10 node gusset plates.
The investigation traced the root cause directly to the original specifications of these specific plates. Reading verbatim from page 152 of the NTSB report, the National Transportation Safety Board determines that the probable cause of the collapse of the I-35W bridge in Minneapolis, Minnesota, was the inadequate load capacity due to a design error by Sverdrup and Parcel and Associates, Inc. of the gusset plates at the U10 nodes, which failed under a combination of 1, substantial increases in the weight of the bridge, which resulted from previous bridge modifications, and 2, the traffic and concentrated construction loads on the bridge on the day of the collapse.
The as-built gusset plates at the U4, U10, and L11 nodes were strictly 0.5 inches thick. This half-inch thickness stood in stark contrast to the structural requirements determined during the post-accident analysis. Demand-to-capacity ratios, or DC ratios, measure the structural stress against the component's maximum yield. A ratio over 1 indicates inadequate capacity. The U10 and L11 gusset plates exhibited DC ratios over 2 for shear, demonstrating a severe lack of necessary thickness. The mathematical inadequacy of these nodes is stated explicitly on page 128 of the NTSB report. Based on the FHW evaluation report, 24 gusset plates at the U4, U4 prime, U10, U10 prime, L11 and L11 prime nodes should have been approximately 1 inch thick, twice their specified 0.5 inch thickness to have acceptable DC ratios.
Physical evidence of this underdesign was visible on the bridge prior to the disaster. Specifically, the half-inch plates were physically distorting. As quoted directly from page 141 of the NTSB report, the Safety Board concludes that the bowing of the gusset plates at the U10 and U10 prime nodes was symptomatic of the inadequate capacity of the plates and occurred under an undetermined load condition before 1999.
Section 4. The 1965 Design Error. The structural failure was traced back to its systemic root cause during the original engineering and certification phases in the 1960s. The design was developed over several years by Sverdrup and Parcel and Associates.
The design timeline reveals critical shifts in material specifications. During a March 1964 conference, the Minnesota Department of Transportation and the Federal Highway Administration directed the designer to eliminate T1 steel from all main truss members. This directive required the redesign of structural members using A44-1 and A242 steels instead. Following these modifications, the final design plans were certified by Sverdrup and Parcel on March 4, 1965, carrying forward the severely undersized 0.5-inch gusset plates into the final blueprints.
The failure to size the plates correctly stemmed from a lack of rigorous quality control within the firm's calculation checks. Detailing this breakdown, page 130 of the NTSB report documents. Although these procedures are more detailed than the earlier ones in terms of the specific individuals who would participate in the review, the overall procedures themselves appear to have changed little. The procedures appear to be sufficient to ensure that calculations receive appropriate levels of review. They also specify the types of calculations necessary for gusset plates, but contain no explicit procedure for ensuring that all necessary calculations are performed.
Section 5. Bridge inspection gaps. This design error was compounded by a complete failure of oversight by both state and federal transportation authorities over the bridge's 40-year lifespan. The I-35W bridge was rated as structurally deficient for 16 years before the accident, yet the extreme vulnerability of the main truss gusset plates remained undetected during every review and inspection.
The investigation established that evaluating gusset plate designs was simply not standard practice during the original plan acceptance. As quoted from page 132 of the NTSB report, the Safety Board concludes that current federal and state design review procedures are inadequate to detect design errors in bridges.
Furthermore, routine field inspections failed to accurately measure the section loss caused by corrosion on the L11 plates, relying solely on visual checks rather than precision tools. On page 151, the NTSB report states, because visual bridge inspections alone, regardless of their frequency, are inadequate to always detect corrosion on gusset plates or to accurately assess the extent or progression of that corrosion, inspectors should employ appropriate non-destructive evaluation technologies when evaluating gusset plates.
Section 6. Findings and Changed Rules. The investigation forced immediate regulatory shifts based on these discoveries. The findings dictated strict new guidelines for design, quality assurance, and load ratings across the industry.
The systemic failures that enabled this tragedy are summarized on page 152 of the NTSB report. Contributing to the accident was the generally accepted practice among federal and state transportation officials of giving inadequate attention to gusset plates during inspections for conditions of distortion such as bowing, and of excluding gusset plates in load rating analyses.
As a direct result of the collapse, the NTSB issued Safety Recommendation H0817 to the Federal Highway Administration, mandating the development of bridge design quality assurance and quality control programs. These programs require verifying that appropriate calculations are performed, ensuring their accuracy, and confirming that structural members have adequate capacity for expected loads. Subsequently, the Minnesota Department of Transportation revised its standard specifications to mandate independent reviews for major bridge designs and instituted strict limits restricting construction material storage on bridge decks to levels commensurate with normal design loads.